Hi guys, this video is about functions in C, and of course by now we have used functions already all the time, beginning with the hello world program where we have a function main, which was calling a function putf or printf for printing a string, and also this video about local and global variables was already dealing with functions and actually details about functions, that functions have their own stack frame where they, for example, store their local variables. And in this video you will see a bit more of the details about functions, so that you, for example, understand how recursive function calls are realized and how functions receive parameters. I want to begin with this simple C program. When you compile it and run it, you will see, of course, that it's printing this character f followed by a new line, b followed by a new line, and then f followed by a new line again. And soon you will also see the very same example in this assembly programming part, and I will give you kind of a preview how we will realize functions there, the first attempt for realizing functions actually. You will see that every function will be realized as a labeled block of code. That means we have a label followed by a sequence of instructions. And now think of this in this case as every statement in this function will be realized by one or more instructions. And of course this put jar function will be realized just by one instruction, our put C instruction. And then in the end, you will see that it is not possible to use a flowchart to actually represent the control flow of this program execution. Now, the function calls will be realized with two instructions. And that means if we begin with the first instruction in function main, it will be loading the address of function foo into a register. And then the next instruction will jump to this stored address. And that means the third instruction is the first instruction of function foo, which then prints this character f. Then the next instruction in function foo is printing this new line. And then the third instruction has to jump back to there, to the first instruction following this function call of foo in function main. So we have to jump back to a certain return address. And there we have the next function call. And again, we have two instructions for realizing this function call, in this case for function bar. We first load the address of function bar into a register, then we jump to this address. That means now the execution flow continues with the first instruction of function bar, which then will print this character b. Then the next instruction there will print a new line, and then we jump back to the return address, which means to the instruction that follows this call of function bar. And this will be again a call of a function, call of function foo again. That means now again we load the address of function foo into a register, jump to this function, and that means now we continue there with printing the character foo, then we print the character new line, and then again we have to jump back. And now this return address is different from the return address of the first function call. Now we jump back to this instruction that follows this second call of function foo in function main, which will actually be this halt instruction in function main. And in C it would be this return 0. And then you see this is not possible to be visualized in the flowchart, because this jumping back to the return address means that we jump back depending on where this function call took place. Now this will be a spoiler for one of the upcoming videos when we deal with functions in assembly programming. You will see that we will not use the jump instructions that we used so far for control structures, for loops and if statements. We will use a special jump instruction, which is actually doing two things. It will of course jump to this address that was previously stored in some register, the address of a function. But before this jump takes place, it also will store the return address in a different register. Now, what is the return address? Well, it's the address of where this jump to this function took place plus 4, because we want to continue after this function call, and because every instruction on the ULM has 4 bytes, it's the instruction pointer plus 4. Now, this will solve the problem of returning to the correct return address. But you will see that it's a bit more complicated when we have functions that call other functions that call other functions, and in particular also might call themselves in recursive function calls, because then we have many return addresses that need to be stored somewhere. And for that, we will use a stack. And on the next slides, I basically will show you how in the end function calls will be realized in our assembly programming part. Another secret is that if you use at least the ULM-C compiler for translating your C program into an executable, function main will not be the first function that gets called when you run this program. And most likely this will be also the case when you use any other C compiler on whatever operating system and hardware you are using. There is a function called _start that on most platforms gets called before function main gets called. And this function, at least on the ULM platform, has the following purpose. It will initialize a so-called stack pointer for this stack data structure. And in the beginning, it will point to the end of the memory. Recall that at the start of the memory, we have our text segment and then the data segment and the BSS segment. So this part of the memory is so far not used. And in the ULM implementation, this will really point to the end of the memory. That means one address beyond the last memory cell. And then this function _start will put on the stack its return address. That means it will decrement this stack pointer by size of the addresses on ULM, 8 bytes, and store there its own return address. And then it calls actually function main. That means after that initialization of the stack and storing its return address there, the execution actually begins with the first instruction of function main. And now function calls will be realized in general like that you decrement the stack pointer and store on this new space, for example, the return address. That means now if function main calls function foo, it will first decrement the stack pointer, put the right return address on this new space that became available, and then this jump gets carried out. And then execution of the instructions in function foo take place. And then after this function is done, it has to return, and for that it will increment this stack pointer and use this return address for jumping back. So after that you basically have the same situation as before. For this function main, now the stack looks as before. At the right hand side of the stack pointer, function main would find the return address to jump back to this _start function. But in this case, of course, we first have to do a few more function calls. So calling function bar again means decrement the stack pointer, store the return address there, then jump to this function bar. Then this statements there will be executed. And after that, it jumps back after incrementing again, of course, the stack pointer. And then we have this second call of function foo, which again means decrementing the stack pointer, storing the return address, jumping to this function, executing these statements. Then it jumps back, and then function main is done. That means now function main will increment the stack pointer, use the return address stored and found there, and jumps back to this _start function. And this _start function in the ULM implementation will hold the program with the return value actually of function main. Now the return value was not really mentioned here, also not parameters that you pass to a function, and also not local variables. So of course on the stack you store a bit more than just the return address. Now these are actually details that you will deal with in programming this in assembly. Here I will just show you that every function has such a small frame on the stack, which it can use for its parameters, its return address, and its local variables. That's what you have to know when you program in C with functions. And still, you will see that certain implementation details that you actually don't have to care with in C programming can be uncovered often by mistake. and I will show you a few examples for that. Okay, let me begin here again from scratch, writing a program foobar in C, and I will use the printf function for printing out some local variables. So this is for int printf const char asterisk and so on. And the function will not have a return value, so return type is void. Function will be called foo, and it also will not get any parameters. And it will have two local variables, a initialized with 42 and b initialized with 1, 2, 3. And then this function just prints the values a and b and also its name. So I am foo, and a is here placeholder for integer, b is placeholder for an integer, new line, a and b. And then I want to also have a function bar. So I just copy that. And now I call this bar. And here I also want to rename the variables, and I will not initialize these local variables. And then I'm changing this here to I am bar, and x and y will be printed out. And then let's also be a bit more precise about function main, that in this case I'm not accepting any arguments. And now I will call function foo first, and then function bar. Now recall from this video about local variables that local variables should be initialized before you use them. So what I'm doing here in function bar is obviously not what I should do. But also notice that in function foo I'm doing everything as I should. I'm initializing them first, and here in function foo I will first, in function main I first will call function foo and then function bar. Now let's see what happens. I will first compile this with my GCC, and also let's turn on all the warnings. Let's see what the compiler will tell us about this code. Okay, warning, initialized. Okay, so this is carrying. Let's recompile it without all warnings. Okay, now I'm less worried, and now we see that for some reason these local variables in function bar do exactly have the same values as they had before in function foo. And of course, it doesn't matter whether you use here the option for all warnings or not. So even if I'm accepting these warnings, of course the executable would do the same. And also if I would use Clang instead of GCC, you will see that it behaves the same. Let's see what the UM compiler is doing with that. Also the same. So kind of interesting that we see here a pattern, although I told you that it's undefined if you use uninitialized local variables. There seems to be a pattern. I will explain you actually what is going on here in a second on the slides. Let me also show you that if you use some optimization flags, which only works for Clang or GCC, you will see a different behavior. Now, let me give you an idea what happened here. Let's say the execution of the program already began, and we are now in function main. And the next thing that will take place is the call of function foo. That means, because we are already in a function call, some part of the stack is already in use, everything on the right-hand side of the stack pointer. And for us, when we do the programming, it seems like the next statement that gets executed is the first statement of function foo. But actually, in between, a few things will be done, where the compiler took care of the gory details. And one thing, for example, is that the compiler makes sure that the stack pointer will be decremented before we continue with function foo. so that function foo has sufficient memory for its local variables. And after all these things were done, we actually begin with the first statement in function foo, where we override this local variable a with a certain bit pattern, with the bit pattern for this value 42. That means some part of this stack frame, the part for this local variable a, will be overwritten, and then in the next statement also the part for variable b. And after that we call function printf, which actually again would generate a stack frame. We skip the details here because they are not relevant. And after printf returned, we return from function foo back to function main. But before we continue with the next statement in function main, again, a few things will be done, where the compiler again took care of the gory details. And one detail is that this stack pointer will be incremented again. And for us, it's like it cleaned up the stack frame, so that we again have the situation as before. This is actually not the case. At least the compiler did not override this stack frame with zeros. So there will be leftovers. That means what was left behind by function foo is still in this memory cells. And now you might guess what happens if we call function bar. Yeah, before we continue with the first statement in function bar, again, the stack frame gets generated by just decrementing the stack pointer. And this will not be somehow overwritten with zeros before the statement gets executed in function bar. And here we actually just have one statement which calls function printf, and it will print the variables x and y, which occupy exactly the same memory locations as variables a and b in function foo. And because nobody has changed these memory cells in between, we still have these previous values. And that was what you saw before. Now, the reason why with these optimizations things were different is that the compiler has a certain freedom for optimizations. For example, in some cases, it's allowed to use registers instead of memory cells for local variables. And that was actually what happened with this optimization.